Okay, now we're going to enter a series of calculations in section 4.3 all the way to 4.6. Okay, and they'll get increasingly more complicated, but they're all going to be useful. They're all very standard, and they will hopefully get you interested in some of the physical applications to thermodynamics. Okay, through heat. The first one we're going to talk about is called thermal expansion. This should be a really intuitive topic, especially since we all live in Saskatchewan, and where we have extremes in temperature, right? We go from really cold to really hot, and if you have noticed that when it gets really hot outside at night, okay, so in the summertime at night you might hear things crack a bit, things expanding and contracting, they make noises. This is due to thermal expansion. Okay, the expansion of metals and materials when they are heated, and their contraction when they are cooled. Let's just talk about metals for the most part, and we're going to talk about linear expansion, which means expansion along one dimension. Okay, certainly three-dimensional expansion is what occurs. However, linear expansion will be enough for us, for our purposes in this class. And you can do some very, very useful things with just linear expansion. So basically, here's this image below is demonstrating a steel rod. Okay, the rod goes up to here, heat is added, and it has expanded outwards. Okay, if you keep adding heat, of course, the molecules, the kinetic energy will be great enough that the electrostatic forces will be broken for the most part, and it will phase change into a liquid, and if you keep adding heat, it will phase change into a gas. But while it maintains a solid, the kinetic energy is moving, so the volume actually will increase slightly, but it will certainly increase. So the amount of linear expansion of a solid depends on two big factors, the initial length and the temperature change, obviously. It is determined, so the change in length, that would be this right here, change in length, is determined via this formula. Change in length is equal to some constant times the initial length times the change in temperature. Okay, what's this constant? Okay, this is called the coefficient of linear expansion. Okay, it's different for different materials, so it varies for different materials. We have a list of alpha, so this is the Greek letter A, alpha, for certain materials on the backside of your thermochemical data table. Okay, which you can see right here. So it would be off to right here. Okay, not too many materials are listed. Aluminum, steel, glass, pyrex, concrete, platinum, copper. Those are your list of coefficient of linear expansion. And the unit for that is degrees Celsius, or 1/4 degrees Celsius, I should say. Okay, so this constant arises, and certainly you can read about this constant. You can go on Wikipedia and type in coefficient of linear expansion, and it will explain to you how it's derived. But basically, different materials will expand at a different rate, okay, depending on the material, and of course the temperature change. But let's suppose you have the same temperature change. So let's suppose you have a, this is basically how it works. Let's suppose you have some steel here. So you weigh out and you measure its length. Then you have, let's say, some aluminum. Never can spell that. And same length. Okay, so if we call this L1 and we call this L2, then L1 is going to equal L2 here. So that's the initial length, so the same. The change in temperature will be the same. So let's say you increase the temperature by 10 degrees. Okay, this guy might increase all the way up to here. This guy would probably only increase up to here. Okay, there's a difference. So delta change in length of the first one is not equal to change in length of the second one. However, you can measure the difference between these two. Okay, you can measure the difference, and for aluminum steel you would have a constant value that would would tell you the relationship between steel and aluminum. This is kind of how alpha is derived, okay? And you can solve for alpha. It is the change in length divided by the initial length over temperature, which is exactly what you would do in this situation. You would measure the change in length and you would determine alpha like that, okay? So, in a brief note, that change in temperature is the final temperature minus the initial temperature. This will be consistent through this whole chapter. So let's do an example. I'm assuming you've read through this example, you've worked through it, read the solution. I'm going to do the practice problem with you. A piece of aluminum house siding is 3.66 meters long on a cold winter day, negative 28 degrees Celsius. How much longer is it on a very hot summer day, 39 degrees Celsius? The coefficient of linear expansion of aluminum is 25 times 10 to the 6 degrees Celsius to the exponent negative 1. Okay, so that last sentence was not necessary. So you can, you're expected to be aware that you're going to have to look that up. So here's aluminums, and the linear expansion is listed here. Okay, but it was listed to you for you here, so that's nice. So what I would do, first of all, you should recognize this is linear expansion because it's asking. First of all, of course, it's giving you the coefficient of linear expansion, but we're talking about how much longer is it with a temperature change. So this indicates linear expansion. Okay. What I would do then is I would copy down the formula. Delta L is equal to alpha times L times change in temperature. Then we are looking for how much longer is it. Okay, how much longer is it at that point? So we're looking for change in length, right? Alpha is equal to 25 times 10 to the 6, negative 6 degrees Celsius to the negative 1. Your initial length is 3.66 meters, and your change in temperature, here's important, is of course the final temperature minus the initial temperature, which in this case is 39 degrees Celsius minus negative 28 degrees Celsius. So your change in temperature will be a positive value. You're effectively going 39 plus 28 to get you 67 degrees Celsius. Okay? Now, you're simply going to plug this into the formula. Okay? Change in length is equal to 25 times 10 to the negative 6. Okay? Sorry, I forgot the unit. Degrees Celsius minus 1 times 3.66 meters times 67. That might cut off, sorry. But the point is, because of this unit and this unit, they'll cancel off to give you meters. So change in length will be in meters here. You're going to have 25 exp negative 6. Sorry about that. Uploading some videos here. Times 3.66 times 67 gives you really, really small length of 0.00613. If you write this in scientific notation, you're going to have we're to two significant figures here, 6.1 times 10 to the negative 3 meters. Okay, so that's how much longer it is on a hot summer's day. Okay. Now, if you wanted to convert that to centimeters, so you can just get a picture of what that looks like, you're going to times that by 100, and that actually comes out to be 0.61 centimeters. So now you can kind of visualize very small expansion, but certainly measurable. Okay, so that's basically thermal expansion. Now, in this example, okay, I went through the same thing. Okay, you might be asked to solve for different variables. So you might be asked to solve for, okay, delta t, or initial length, given the other ones. So expect that. If I ask you to solve for this one, okay, alpha, if I ask you to solve for the coefficient of linear expansion, don't reference the table if that's the case. Okay, it rarely will be the case, but use the values that I give you and go from there. Okay, because it might be an experimental problem where the alpha might not match this table precisely, but certainly if we were to do this in a lab procedure, which we could do, then your value of alpha certainly might not match this. And I think that's about it. Okay, so certainly another thing I could just say before this video ends is when it asks how much longer it is on a hot summer's day, if it asked for the final final length, if asked for final length, okay, that is not change in length. Okay, final length, and I'll perhaps put it in a totally different color. Final length, whoa, what in the world? Sorry. Final length is equal to L plus change in length, right? The initial plus the change. So keep that in mind as well. So with that, do some of the practice problems and then move on to the next formula in section 4.4.